The Earth was once home to many dinosaurs. Some of these dinosaurs had very long necks that helped them reach leaves high above the ground. Others had extremely long bodies. Many of them were also very heavy. They lived millions of years ago, in a time when the Earth was warmer and covered with forests and open land. During this period, some dinosaurs grew to sizes that no land animal has reached since. What made these ancient giants feel bigger, wilder, and full of wonder? Argentinosaurus was one of the most enormous creatures ever to walk on land. It lived during the late Cretaceous period in what is now Argentina, at a time when dinosaurs ruled the earth and the land was filled with a wide variety of strange and powerful animals. Even though scientists have only found a limited number of its bones, Argentinosaurus still stands out as one of the largest dinosaurs ever discovered, and possibly the largest of all. This giant animal could grow to a length of about 30 to 35 meters and weigh between 65 and 80 tons. To put that into perspective, it was longer than a basketball court and far heavier than the largest elephants alive today. Argentinosaurus belonged to a group of long-necked dinosaurs known as Titanosauria. These dinosaurs were the dominant plant eaters of the Cretaceous period. They were known for their long necks, long tails, and huge bodies supported by thick, pillar-like legs. Titanosaurs were very successful and lived all over the world, but Argentinosaurus was one of the biggest members of this group. Its long neck allowed it to reach high into trees or sweep across large areas of vegetation, feeding on massive amounts of plant material every day to support its gigantic size. The discovery of Argentinosaurus began in the year 1987, when a farmer named Guillermo Heredia found a large, unusual object on his land. His farm, called Las Overas, was located about 8 kilometers east of the city of Plaza Huincul. At first, he believed the object might be a piece of petrified wood, something that is not uncommon in fossil-rich areas. However, he decided to report the find to the nearby Museo Carmen Funes. This decision would turn out to be very important. In the year 1993, José Bonaparte and another Argentine paleontologist, Rodolfo Coria, officially described and named the new dinosaur. They gave it the name Argentinosaurus huinculensis. The first part of the name means Argentine lizard, while the second part honors the town of Plaza Huincul, where the fossils were found. This formal naming marked the moment when Argentinosaurus became recognized as a unique and important species in the scientific world. Over time, additional bones were discovered at the same location. These included a complete femur or thigh bone and parts of another. These bones were extremely large, matching the size expected for such a giant dinosaur. However, some of these fossils were damaged or deformed during the long process of fossilization. For example, one of the thigh bones had been flattened from front to back by the pressure of the surrounding rock over millions of years. This made it more difficult for scientists to study its original shape. Because the remains of Argentinosaurus are incomplete, scientists have faced many challenges in understanding this animal. They have had to rely on comparisons with other, better-known titanosaurs to fill in the missing pieces. There has been ongoing debate about how its backbone was arranged and how its massive body was supported. Some scientists have suggested that special joints between the vertebrae helped strengthen the spine, allowing it to carry such enormous weight without collapsing. To learn more about how Argentinosaurus might have moved, scientists have used computer models to recreate its body and muscles. These models suggest that, despite its size, Argentinosaurus was capable of steady movement. However, it was not fast. Its top speed is estimated to have been about 7 kilometers per hour. It likely walked using a gait in which the front and back legs on the same side of its body moved together, creating a slow but powerful stride. The fossils of Argentinosaurus were found in a geological formation known as the Huincul Formation. This rock layer was formed between about 97 and 93.5 million years ago, during the middle part of the Cretaceous period. At that time, the area was a rich and active environment, filled with rivers, plants, and many different kinds of animals. Among the creatures that lived alongside Argentinosaurus was the giant meat-eating dinosaur Mapusaurus. This predator was one of the top hunters of its time and may have posed a threat, especially to young or weak individuals. The presence of such large predators shows that Argentinosaurus lived in a complex and sometimes dangerous ecosystem, where survival depended on size, strength, and perhaps living in groups. As research has continued, scientists have sometimes revised their understanding of the fossils. For example, the very first bone discovered was originally thought to be part of the shin, but later studies showed that it was actually a fibula, a thinner bone in the lower leg. Other bones, such as the femurs found later, have also been studied carefully, but there is still some uncertainty about whether all of them truly belong to Argentinosaurus. Over the years, scientists have made many different estimates of how long Argentinosaurus was. In the year 1994, a researcher named Gregory Paul suggested it could have been between 30 and 35 meters long. Later in that same year, José Bonaparte and Rodolfo Coria gave more detailed measurements. They estimated that its back leg alone was about 4.5 meters long, the main body from hip to shoulder was about 7 meters, and the whole animal stretched to about 30 meters in length. As more studies were done, these numbers continued to change. In 2006, Kenneth Carpenter used a better-known relative called Saltosaurus as a guide and again estimated a length of about 30 meters. 2 years later, Jorge Calvo and his team compared it with another giant dinosaur, Huincul, and suggested it might have been a little under 33 meters long. Then, in 2013, William Sellers and his team carefully measured a mounted skeleton in the Museo Carmen Funes and came up with a much larger estimate of about 39.7 meters in length, with a shoulder height of about 7.3 meters. Not all scientists agreed with such large numbers. In that same year, Scott Hartman argued that Argentinosaurus may have had a shorter tail and a narrower body than some other giant titanosaurs, which would make it slightly smaller. Later, in 2016, Gregory Paul returned to a more moderate estimate of about 30 meters. But by 2019, after comparing it with other giant South American dinosaurs, he suggested it could have reached about 35 meters or even more, especially when its missing neck and tail were fully reconstructed. Estimating its weight has also been a challenge, and different scientists have suggested different values. In 1994, Gregory Paul estimated that Argentinosaurus could have weighed between 80 and 100 tons. In 2004, another group of researchers suggested a range between 60 and 88 tons, with about 73 tons being the most likely value. In 2013, Sellers and his team calculated a mass of about 83.2 tons using a detailed model of the skeleton. Later studies gave even higher numbers. In 2014 and again in 2018, Roger Benson and his colleagues estimated weights of about 90 and 95 tons, although these figures were questioned because they had a large margin of error. In 2016, another team used equations based on the size of limb bones and suggested a mass of about 96.4 tons, though it is not completely certain that the bone they used actually belonged to Argentinosaurus. At the same time, some scientists began to lower earlier estimates. Gregory Paul, in 2016, suggested that it may have weighed more than 50 tons, which was much less than his earlier estimate. By 2019, he refined this further, proposing a weight between 65 and 75 tons based on detailed skeletal drawings. In 2020, another study arrived at a similar figure of about 75 tons. By 2023, newer research suggested that the known specimen of Argentinosaurus may have reached between 75 and 80 tons at its largest. Some scientists even proposed that another poorly known dinosaur, Brachiosaurus, might have been heavier still, possibly reaching between 110 and 130 tons. Even though Argentinosaurus was clearly enormous, scientists still debate whether it was truly the largest of its kind. Other giant dinosaurs such as Puertosaurus, Feudaloncosaurus, Dreadnoughtus, Paralidoton, Antarctosaurus giganteus, and Alamosaurus have all been suggested to be similar in size in some studies, while other research has found them to be smaller. In 2017, one study suggested that Patagotitan might have been bigger based on the structure of its spine, but in 2019, Gregory Paul argued that Argentinosaurus was still larger because its back was longer. There is also the possibility that some other sauropods, like Maraponisaurus or certain very large Mamenchisaurids, could have been even bigger, although they are known from only a few bones, making it hard to be sure. Some long-bodied dinosaurs such as Supersaurus and Diplodocus may have been longer than Argentinosaurus, but they were much lighter and less massive. Despite all this, none of these land animals come close to the size of the modern blue whale, which can weigh more than 150 tons and remains the largest animal ever known. The bones of Argentinosaurus themselves show just how huge it was. Like other titanosaurs, it likely had about 10 back vertebrae. These bones were enormous even compared to other giant dinosaurs. One of its back vertebrae is estimated to have been about 159 centimeters tall and 129 centimeters wide, with the central part of the bone reaching up to 57 centimeters across. In 2019, Gregory Paul estimated that the full length of the backbone in this region was about 447 centimeters. He also suggested that the hips were very wide, measuring about 60% of the combined length of the back and hip vertebrae. The shape of these bones is also important. The back vertebrae were slightly hollowed at the back, a feature seen in similar dinosaurs. On the sides of the vertebrae were small openings called pleurocoels, which were positioned toward the front. Inside, the bones were filled with many air pockets, making them lighter without losing strength. This kind of bone structure is especially common in the largest, long-necked dinosaurs and helped them support their massive bodies. The ribs of Argentinosaurus were long and tube-like, forming a strong but relatively light rib cage. Some early researchers believed the ribs were hollow, although later scientists suggested this might have been caused by damage after the animal died. Like many titanosaurs, it probably had 6 fused vertebrae in its hip area, although not all of them have been found. These hip bones show that some of the vertebrae were much smaller than others, and the ribs in this region curved downward to support the body. Over the years, several scientists have suggested their own ideas about how these bones should be arranged. In the early 1990s, José Bonaparte and Rodolfo Coria proposed one arrangement. Later, in the mid-2000s, Fernando Novas and Martín Ezcurra suggested a different order. Then, around the early 2010s, Leonardo Salgado and Jaime Powell offered yet another interpretation. Each group looked at the same bones, but came to different conclusions about where they belonged in the spine. For example, one particular vertebra has been identified in different ways depending on the study. Some researchers believed it was the very first bone in the back, while others thought it might be the third or even the fifth. Another bone caused even more confusion, as it has been labeled as the second, the ninth, the 10th, or even the 11th vertebra by different scientists. A fairly complete bone was considered the third vertebra in some studies, but another group argued it was actually the fourth. Yet another bone was thought to belong near the back end of the spine, though exactly which position it held also differed depending on the interpretation. Even a pair of vertebrae that were found still connected to each other added to the debate. At first, they were believed to come from the rear part of the back, but later studies suggested they were actually the 6th and 7th bones in the sequence. On top of all this, one later study even mentioned an additional vertebra that had not been discussed at all in earlier research, and this bone was also believed to come from the rear portion of the spine. All of this shows just how difficult it is to rebuild a giant dinosaur's skeleton when only scattered pieces are available. Another area of disagreement involves special structures between the vertebrae known as hyposphene-hypantrum articulations. These are extra joints that sit below the main contact points between the bones and help strengthen the spine. Studying these features is especially challenging because the fossils are broken and incomplete, and in some cases the important parts are hidden from view, especially in the vertebrae that are still joined together. In the early 1990s, Bonaparte and Coria suggested that these extra joints were large and well-developed, similar to what is seen in a related dinosaur called Epacthosaurus. They believed these joints had extra surfaces that extended downward, making the connections between the bones stronger. Later researchers supported this idea. One scientist explained that part of the joint extended sideways and downward, creating a broad surface that locked together tightly with a matching structure on the next vertebra. By the mid-1990s, it was suggested that these strong connections would have made the dinosaur's spine more rigid, possibly helping it support its enormous body. However, not all scientists agreed. Some argued that most titanosaurs did not have these special joints at all. Instead, they believed that the structures seen in Epacthosaurus and Argentinosaurus were actually just thickened ridges of bone, rather than true joints. In the mid-2000s, Sebastián Apesteguía supported this second idea, suggesting that these features were modified ridges that served a similar purpose, helping to strengthen the spine even if they were not exactly the same as the original joint structures. The leg bones of this giant dinosaur also give an idea of its incredible size. A complete thigh bone, known as the femur, measures about 2.5 meters in length. Around its narrowest point, the bone is still very thick, with a circumference of a little over 1 meter. Scientists have used mathematical methods to estimate its full original length, and their results are very close, suggesting it was just over 2.5 meters long. Later estimates reached almost the same conclusion. When compared to other enormous titanosaurs, this femur is slightly longer. For example, the thigh bones of Antarctosaurus giganteus and Patagotitan majorum are both a bit shorter. Even though the main specimen of this dinosaur does not include a femur, it does include a long, slender lower leg bone called the fibula, which measures over 1.5 meters in length. At first, scientists thought this bone was actually a tibia, but later studies showed that it lacks the key features of a tibia and instead closely matches the shape of fibulae found in other long-necked dinosaurs. The group it belongs to, called Titanosauria, is one of the least clearly understood groups of dinosaurs. For a long time, most fossils from this group were placed into a single family known as Titanosauridae, a name that has been used since the late 19th century. However, as more discoveries were made, scientists began to question whether this grouping really made sense. When Argentinosaurus was first described, it was noted to be different from typical members of this family because of the supposed presence of the special spinal joints. Since these features were also seen in Ankylosaurus and Apacthosaurus, a new family was proposed to include all three. This new family was later grouped together with Titanosauridae under a larger category called Titanosauria. As time went on, new studies kept changing the picture. Some researchers placed this dinosaur within Titanosauridae alongside other species, while others included it in different groups with dinosaurs such as Opisthocoelicaudia and Lorrainosaurus. Later studies even suggested that some of these families were not valid at all, arguing that they were based on unclear or primitive features rather than strong defining traits. In the early 2000s, a new group called Lithostrotia was introduced, which included more advanced titanosaurs. In this classification, Argentinosaurus was placed outside this group, meaning it was considered more primitive. Many later studies supported this idea, but the debate did not end there. In the late 2000s, a new dinosaur called Futuloncosaurus was discovered, and it was grouped together with Mendozasaurus into a new branch called Loncosauria. Later research suggested that Argentinosaurus also belonged to this group and was closely related to Patagotitan majorum. Some studies even placed this group within Lithostrotia, while others disagreed. By the late 2010s, scientists were still debating its exact position. Some studies placed it as a more primitive member of Titanosauria, while others grouped it again within Loncosauria. There were even suggestions that certain related groups might lie outside Titanosauria altogether. Another study introduced a larger grouping called Colossosauria, which included Loncosauria, along with another branch known as Reconstructing. The enormous size of Argentinosaurus and other long-necked dinosaurs, known as sauropods, did not happen by chance. It was likely the result of several powerful advantages working together over millions of years. One of the most important of these was their long neck. With such a neck, they could reach a wide area of plants without having to move their heavy bodies too much. This made feeding faster and saved a lot of energy. Unlike many animals today, they did not chew their food, a process known as mastication. Instead, they swallowed plants whole, allowing them to eat quickly and in large amounts. Another key advantage was how they grew and reproduced. These giant animals likely grew very quickly from a young age, and they produced many small offspring instead of a few large ones. This meant that even if many young did not survive, enough would grow into adults to keep the population stable. Being so large also gave them major survival benefits. Their huge bodies allowed food to stay longer in their digestive system, giving them more time to extract as much energy as possible. At the same time, their size made it much harder for predators to attack them successfully. Like many reptiles, sauropods laid eggs. In 2016, scientists Mark Hallett and Matthew Weddell suggested that the eggs of Argentinosaurus were surprisingly small for such a massive animal, holding only about 1 liter. From these eggs hatched tiny young that were no longer than about 1 meter and weighed no more than about 5 kilograms. From such small beginnings, Argentinosaurus underwent an astonishing growth journey, increasing its body size by many orders of magnitude as it matured. more than what is seen in any other group of animals that lay eggs on land. According to their estimates, Argentinosaurus may have reached sexual maturity at around 8 to 10 years of age. It likely continued growing until about 20 years old, when it reached full physical maturity, and may have lived for roughly 30 years. Interestingly, as these giant plant eaters evolved to become larger and larger, their predators also seemed to grow in size. One of the main threats to Argentinosaurus may have been Mapusaurus, one of the biggest meat-eating dinosaurs known. Fossils of at least 7 individuals of Mapusaurus have been found together, which raises the possibility that they hunted in groups. Working as a team, they might have been able to attack even a giant like Argentinosaurus. In 2013, researcher William I. Sellers and his team used advanced computer models to better understand how Argentinosaurus moved. Before this, scientists could only guess dinosaur speeds by studying their bones and fossil footprints. For this new approach, the team created a digital model of the skeleton and muscles, based on a detailed laser scan of a mounted skeleton displayed at the Museo Carmen Funes. They compared its muscles to those of living animals and estimated a body mass of about 83 tons. Using computer simulations and machine learning, the digital Argentinosaurus was tested to see how it could move while using the least amount of energy. The most efficient walking style turned out to be a slow, steady pace, where the front and back legs on the same side of the body moved together. Even at its fastest, it could only reach a speed of just over 2 meters per second, which is about 7 kilometers per hour. This shows that despite its immense size, it was not built for speed, but for steady movement. The researchers concluded that Argentinosaurus may have been close to the maximum practical size for a land animal with that kind of body structure. Larger land animals might have been possible, but they would likely need very different body designs or behaviors to avoid putting too much stress on their joints. However, the scientists also noted that their model was still quite simple and not perfectly realistic. To improve it, more information from living animals and better fossil evidence would be needed. A more recent study from 2025 suggested a slightly slower walking speed of about 1.58 meters per second, which is around 5.7 kilometers per hour. Even so, this reinforces the same idea. Argentinosaurus was a slow but powerful giant, built not for chasing or escaping quickly, but for enduring life at a massive scale. Argentinosaurus was first discovered in a part of Huincul province, a region known for its rich and ancient fossil beds. At the time of its discovery, scientists believed the fossils came from a rock layer called the Rio Lime Formation, which was thought to be part of a larger geological grouping known as the Huincul group. However, as research improved and scientists took a closer look, they refined this classification. Today, those same rocks are more accurately known as the Huincul Formation, which itself belongs to the Rio Lime subgroup, a smaller division within the much larger Huincul group. This entire region lies within the vast Huincul Basin in Patagonia, an area that, millions of years ago, looked very different from the dry landscapes seen today. The rocks of the Huincul Formation are made up mostly of sandstones that appear yellowish and greenish in color. These sands are fine to medium in size, and some of them contain volcanic ash, showing that volcanic activity once played a role in shaping this environment. These layers of rock were formed during the later part of the Cretaceous period, a time when dinosaurs still ruled the land. Scientists believe these sediments were laid down sometime between the middle of the Cenomanian stage and the early part of the Turonian stage, or possibly from the early Turonian all the way to the late Santonian stage. In simpler terms, this means the environment existed roughly between about 100 million and about 84 million years ago. Back then, the land was shaped by a wide, branching river system, known as a braided river, where multiple streams split and rejoined, constantly shifting and depositing sand and mud across the landscape. Tiny fossilized grains of pollen found in these rocks tell an even richer story about what life was like. These microscopic remains show that the area supported a wide and diverse range of plants. There were simple plants like hornworts and liverworts, along with ferns and members of the Selaginellales group. There may even have been plants related to the mysterious Noagarrathiales. Larger plants also thrived, including gymnosperms such as conifers and netophytes, as well as angiosperms, which are flowering plants. Some pollen grains are so unusual that scientists still cannot clearly identify what plants they came from. The Huincul Formation is not only rich in plant life, but but also one of the most important fossil sites in Patagonia for animal remains. It preserves a wide range of vertebrates, meaning animals with backbones. Among them were fish like lungfish and gar, as well as turtles belonging to the chelid group. There were also reptiles such as squamates, which include lizards and snakes, and sphenodonts, relatives of the modern tuatara. Crocodile-like animals known as neosuchians also lived in this environment. Most impressively, this formation is filled with dinosaur fossils. In fact, the greatest number of these fossils is usually found in the lower layers of the formation, which are also the oldest. This suggests that the earlier periods of this environment were especially rich in life, or better at preserving it. Alongside Argentinosaurus, several other long-necked plant-eating dinosaurs, known as sauropods, lived in this region. One of them was Choconsaurus, another giant titanosaur. There were also members of a different group of sauropods called Brachiosaurids, including Cathartosaura and Limaesaurus, along with several species that have not yet been given names. The land was not only home to peaceful plant-eaters, it was also filled with powerful meat-eating dinosaurs, known as theropods. Among them was Mapusaurus, a massive predator related to some of the largest carnivores ever known. Other hunters included Scorpiovenator, Elocolesia, and Tralcosaurus. Smaller but still agile predators were also present, such as Huincul. Bird-like dinosaurs, known as paravians, were represented by Oviroraptor, while other theropods like Aeoniraptor and Gualicho added even more diversity to this ancient ecosystem. In addition to all these creatures, plant-eating dinosaurs similar to iguanodonts also roamed the area, feeding on the rich vegetation that grew along the rivers. Altogether, the Huincul Formation paints a vivid picture of a thriving prehistoric world, one filled with rivers, lush plant life, and an incredible variety of animals, from small reptiles to some of the largest dinosaurs that ever walked the earth. Patagotitan is a giant dinosaur that belonged to a group called Titanosaurs, which were long-necked, plant-eating sauropods. It lived during the early Cretaceous period, specifically in the Albian stage, in an area now known as Chubut Province, in the southern region of Patagonia, Argentina. This dinosaur is known from only one species, called Patagotitan majorum, which is based on fossils from at least 6 young adult individuals. The discovery was first announced in 2014 and officially named in 2017 by paleontologists José Carballido and his team. When first studied, Patagotitan was thought to be the largest titanosaur and possibly the largest land animal ever. Early reports suggested it could have reached a length of 37 meters, which is about 121 feet, and might have weighed around 69 tons, equivalent to 76 short tons. Later studies, however, revised these estimates. Scientists now think it was closer to 31 meters long, or about 102 feet, and weighed roughly between 50 and 60 tons, which is about 55 to 66 short tons. This means that while Patagotitan was enormous, it may have been similar in size, or slightly smaller, than its closest relatives, Argentinosaurus and Portosaurus. Despite this, Patagotitan is one of the most well-known titanosaurs, and scientists have been able to consistently place it within the titanosaur family tree. In fact, its study helped redefine a group of giant titanosaurs known as Colossosauria in 2020. Like Argentinosaurus and other members of the Loncosauria group, Patagotitan was especially large and solidly built. It can be told apart from its relatives by several unique features in its skeleton, including the vertebrae in its back and tail, the shoulder bones, scapulae, and forelimb bones, humeri, and the hip and leg bones, including the ischia and femora. One unusual feature was a special connection between 2 back vertebrae near the shoulder blade, called hyposphene hypantrum articulations. This feature was probably used to support its massive weight and is not seen in other sauropods, which either had these connections between all vertebrae or none at all. Patagotitan also had distinct markings on its limbs that were likely attachment points for strong muscles. It lived in a forested floodplain environment filled with conifer trees, providing both shelter and food. The first piece of Patagotitan was found in 2010 when a farm worker named Aurelio Hernandez discovered part of a lower thigh bone in the desert near La Flecha, Argentina. This location is roughly 250 kilometers, or 160 miles, west of the city of Trelew. Hernandez reported the find to P. Huerta at the Museum of Paleontology Egidio Ferruglio in Trelew. A preliminary field expedition visited the site in late 2012, followed by 7 more expeditions between January 2013 and February 2015. These efforts uncovered more than 200 fossils, including 130 sauropod bones and 57 teeth from carnivorous theropod dinosaurs. The rock layers where the fossils were found belong to the Cerro Castaño member of the Cerro Barcino Formation, which has been dated to about 101,620,000 years ago in the latest part of the Albian stage. The sauropod fossils were grouped into 6 partial skeletons, all similar enough in shape and size to suggest they belonged to the same species, with no individual differing by more than 5% in length. Even though all the bones were found in the same quarry, the dinosaurs likely did not die at the same time. The fossils were spread across a sediment layer about 3 meters and 43 centimeters thick, which contained 3 separate levels of burial. In 2017, the fossils were officially named as a new species, Patagotitan majorum, by José Luis Carbalido, Diego Pol, Alejandro Otero, Ignacio Alejandro Cerda, Leonardo Salgado, Alberto Carlos Garrido, Jahandar Ramezani, Nestor Ruben Cuneo, and Javier Marcelo Kraus. With these discoveries, Patagotitan became one of the most completely known titanosaurs. Its name combines a reference to Patagonia with the Greek word titan, highlighting the dinosaur's massive size and strength. The species name honors the Mayo family, who own the La Flecha Ranch where the fossils were found. Today, skeletal reconstructions of Patagotitan can be seen in several museums around the world. Research Casting International created digital scans of the bones, followed by foam molds, fiberglass casts, and 3D printed models. One full mount is on display at the Museum of Paleontology Egidio Ferruglio. Another is at the American Museum of Natural History, where it replaced a juvenile Brachiosaurus display. Some original fossils, including a femur, were briefly displayed there as well. The Field Museum of Natural History in Chicago also has a mount, which replaced the famous Tyrannosaurus specimen known as Sue. From March 2023 until January 2024, a Patagotitan mount was exhibited at the Natural History Museum in London, sharing the story of these enormous creatures with visitors across the world. Patagotitan was one of the enormous titanosaur sauropods, a group of long-necked, long-tailed dinosaurs that walked on all 4 legs and ate plants. Like its relatives, it had a very long neck and tail, which allowed it to reach high into trees for food or sweep the ground for low vegetation, and it is particularly famous for its immense size, which made it one of the giants of the dinosaur world. When Patagotitan was first introduced to the public through news reports in the year 2014, scientists estimated that it could reach around 40 meters in length, which is about 131 feet, and could weigh up to 77 tons, equivalent to about 85 short tons. A few years later, in 2017, paleontologist José Carbalido and his team published a more detailed study. They suggested that Patagotitan was slightly shorter, at about 37 meters in length, or 121 feet, but they provided 2 different weight estimates. Using a scaling formula based on known bones, they calculated around 69 tons, which is roughly 76 short tons. Using a volumetric method based on 3-dimensional skeletal models, they suggested a weight range from 44.2 to 77.6 tons, or approximately 43.5 to 76.4 long tons, equivalent to 48.7 to 85.5 short tons. According to these figures, Patagotitan might have been around 10% larger than the massive Argentinosaurus. In 2019, Gregory S. Paul offered a more conservative estimate. He suggested that Patagotitan was about 31 meters long, which is roughly 102 feet, and weighed between 50 and 55 tons, or 49 to 54 long tons, and 55 to 61 short tons. By this calculation, it appeared slightly smaller than Argentinosaurus, which Paul estimated to be more than 35 meters in length, or 115 feet, and weighing between 65 and 75 tons, or 64 to 74 long tons, equivalent to 72 to 83 short tons. In 2020, researchers Campione and Evans suggested a body mass of approximately 55.7 tons, or 54.8 long tons, about 61 short tons. In the same year, Otero and Carbolito published a slightly lower average weight estimate of 57 tons, or 56 long tons, around 63 short tons, with a margin of error from 42.5 to 71.4 tons, or 41.8 to 70 long tons, equivalent to 46.8 to 78.7 short tons. This estimate closely matched the volumetric estimate from 2017. Bone studies, specifically examining 5 thigh bones and 1 upper arm bone, show that the Patagotitan individuals that were found died while still young adults. Their growth had slowed down but had not completely stopped, suggesting they were still capable of gaining size if they had lived longer. In 2024, Gregory Paul again estimated Patagotitan to be 31 meters long, about 102 feet, with a weight of 57 tons, or 56 long tons, around 63 short tons. In 2025, Matthew Dempsey suggested an even heavier weight of over 60 tons, which is roughly 59 long tons and 66 short tons. After Patagotitan's official description in 2017, some experts urged caution regarding the size estimates. Science writer Riley Black and paleontologist Matt Weddle noted that, based on the bones available, Patagotitan was similar in size to other enormous titanosaurs, but almost every measurable bone in Argentinosaurus was larger. Weddle also criticized the method Carbolito's team used to compare vertebrae sizes, which involved a polygon-based calculation, because Patagotitan's bones had large empty spaces that might have skewed the results. Other studies have estimated Argentinosaurus at between 65 and 96.4 tons, which is around 71.7 to 106.3 short tons. In 2019, Paul pointed out that the back vertebrae of Argentinosaurus measured 4.47 meters, about 14.7 feet, while Patagotitan's measured only 3.67 meters, about 12 feet. This made it unlikely for Patagotitan to have a larger torso, without its other body parts being improbably enormous, or vice versa for Argentinosaurus. Paul also criticized the three-dimensional volumetric model, noting that it had a flat-sided torso, with the neck and tail reconstructed as unusually long. Looking closer at Patagotitan's bones, the vertebrae in the front and middle parts of its neck were very long, at least 5 times longer than they were wide at the back. The tops of these vertebrae had flattened spines, and there were only small holes on the sides, with no large openings. In contrast, the rear neck vertebrae had deep side openings that connected to the interior of the bone. Whether the tops of these rear vertebrae were expanded horizontally, like those of other titanosaurs such as Huincul, Ligabuosaurus, and Mendozasaurus, cannot be determined from the fossils. Patagotitan, like Huincul and other titanosaurs with complete backbones, likely had 10 back vertebrae. Several features of these vertebrae were unique. The laminae, or ridges crossing the bones, were thin but very pronounced, unlike in Argentinosaurus or Portosaurus. One special feature was the prezygote apophyseal laminae, or PRDLs, which ran between the front and side joints of each vertebra. In Patagotitan, these ridges were almost vertical because the front joints were higher than the side joints, while in most other sauropods, these ridges sloped forward. The neural spines along the back were tall and vertical, and the first few ended in wide, arrow-shaped tips. Argentinosaurus had arrow-shaped tips too, but its back spines slanted backward, a typical condition in the larger group Titanosauriforms. Patagotitan's pattern represented a return to a more primitive condition. Some other titanosaurs like Dreadnoughtus and Brachiosaurus had short front spines without arrow-shaped tips. A few vertebrae also had unusual features. The first 2 back vertebrae had laminae bulging outwards near the base, and the third vertebra had a hyposphere at the rear, but not a hypantrum at the front. The missing 4th vertebra likely had a matching hypantrum. Hyposphere-hypantrum articulations, which help stiffen the spine, were common in early sauropods, but lost in many later species. Patagotitan is the first known sauropod to have this feature preserved in only a single vertebral pair, possibly because the shoulder blade rested there, indicating a weight-bearing adaptation. Patagotitan's tail also had unique traits. Most titanosaurs had tail vertebrae that were concave in the front and convex at the back, but Patagotitan's first tail vertebra had a flat front surface. The spines on the front tail vertebrae were unusually wide, about 4 to 6 times wider than they were long, and were taller than the vertebral bodies beneath them. The tops of these spines were concave, slightly splitting and curling forward. Longitudinal laminae on these spines were separated from the usual prespinal and postspinal laminae, a trait only seen previously in Bonitosaura. The side processes of the tail vertebrae were high and thin, like in Futaloncosaurus and Mendozasaurus, rather than forming wing-like shapes like in Diplodocids. These features allowed for larger attachment areas for the tail muscles, making the tail stronger and more muscular. Well-developed spinodiapophyseal laminae also ran from the spines down to the side processes, similar to other giant titanosaurs, contributing to a powerful and functional tail. Patagotitan had a very strong and broad shoulder blade, called a scapula, which was unusually wide for its length compared to most of its close relatives in the group Macronaria. Specifically, the blade was just over 4 times as long as it was narrow at its thinnest point, a proportion that only a few other titanosaurs, Drusilla, Isosaurus, Nuconsaurus, and Saltosaurus, shared. Both ends of the scapula were expanded, so that the top and bottom were almost level with each other, a rare feature also seen in Isosaurus. Like other titanosaurs, the acromion ridge, a bony crest along the scapula, was about 30% as long as the scapula itself. Patagotitan also had a small projection near the bottom of the scapula, just behind the shoulder joint, known as the glenoid, which was typical of titanosaurs. Interestingly, there was a second projection further back at the start of the blade, a feature shared only with Alamosaurus, Dreadnoughtus, Drusilla, Elaltitan, and Sauropods. The scapula also had 2 ridges running along it, one along the midline parallel to the bottom edge, and a second running diagonally toward the top. This diagonal ridge was unique to Patagotitan. The surface where the scapula joined the coracoid bone was quite unusual, being 80% as long from front to back as it was tall, a trait otherwise seen only in Giraffitan, Ruyangosaurus, and Tapuiosaurus. The sternal plates of Patagotitan, which are part of the chest, were crescent-shaped, like those of other titanosauriforms. Their outer edge curved inward only slightly, similar to Dreadnoughtus and Savannosaurus, whereas in the Saltosauridae family, this curve was much deeper. A ridge ran diagonally from the outer bottom corner of each plate, oriented in a way similar to Dreadnoughtus and Opistheculicaudia. The humerus, or upper arm bone, was very thick and sturdy, being just over 1/4 as wide as it was long. This made it comparable to the humerus of Notocolossus and Rapidosaurus, though less massive than those of the Saltosaurids. Like Dreadnoughtus, Apacthosaurus, and Opisthecuelicaudia, the humerus measured roughly 70% the length of the femur, or thigh bone. Patagotitan had several unique bumps and ridges on the humerus for muscle attachments. On the front upper part, there was a shallow depression holding 2 scars, one above the other, where the coracobrachialis muscle attached, the top scar being wider than it was tall, and the bottom scar taller than it was wide. On the outer side behind the deltopectoral crest, another pair of scars marked where the supracoracoideus, deltoideus clavicularis, and latissimus dorsi muscles connected. The ulna, one of the forearm bones, was also strong, being about half as wide at the top as it was long, similar to Dreadnoughtus, Isosaurus, Nuconsaurus, Opistheculicaudia, and Saltosaurus. Its inward-pointing process was slender, 3.5 times longer than it was wide, and slanted about 40 degrees, differing from Nuconsaurus in both aspects. The bottom end of the ulna was slightly expanded, though not as much as in Opistheculicaudia and Saltosaurus. The radius, the other forearm bone, was moderately wide as well, about 36% as broad at the top as it was long. A bulge along its inner edge formed a crest for the biceps brachii muscle, extending toward the front, a feature shared only with Elaltitan. Other dinosaurs like Giraffitan and Hastosaurus had the bulge but not the crest. The hip bones of Patagotitan had some unique features too. The pubis and ischium, pointing forward and backward respectively, overlapped along about half the length of the pubis, a longer overlap than in Dreadnoughtus, Futaloncosaurus, Muilensaurus, and Chaowanlong. The contact between the pubic bones was clearly separated from their connections to other bones by deflected surfaces, similar to Alamosaurus and Elaltitan. A ridge ran along the side of the pubis, fading near the elongated obturator foramen at the top, as seen in Uberabatitan. Unlike Alamosaurus, the bottom of the pubic boot was not especially widened, a trait shared with Elaltitan and Futaloncosaurus. The ischium had a strong ridge running down its side from the ischial tuberosity to the blade, a feature present but less pronounced in Ankylosaurus, Junction-osaurus, and Venenosaurus. The combination of these features in the hip was unique to Patagotitan. The femur, or thigh bone, was just as robust as the humerus, being nearly a quarter as wide as it was long. This made it similar to Brachiosaurus, but slightly less massive than those of Diamantinosaurus, Opisthochelocaudia, and Saltosaurus. The head of the femur angled upward relative to the greater trochanter at its top outer end, as in other titanosauriforms. A ridge ran along the back of the femur between the head and the trochanter, a trait shared with Nuconsaurus and Rapidosaurus, though there was no corresponding ridge on the front side, like in Alamosaurus, Diamantinosaurus, and Saltosaurines. The fourth trochanter, a bony projection on the inner surface, was located about a third of the way down from the top instead of halfway, as seen in Bonitosaura, Nuconsaurus, Rapidosaurus, and Saltosaurus. Patagotitan also had a series of coarse ridges along the outer edge of the lower femur, right above the joint known as the lateral condyle. This was where the flexor digitorum longus muscle attached, a feature unique among sauropods. In the year 2017, a detailed study of dinosaur relationships conducted by Carbolito and his team revealed that Patagotitan was most closely related to its giant cousin, Argentinosaurus. The two titans were linked by a unique feature in their front-back vertebrae, long, towering neural spines. These two enormous dinosaurs were placed in a special subgroup of titanosaurs called the Logoncosauria. This group was identified by several distinctive traits, including the shape of certain tail vertebrae bones, which had tall sideways extensions and small bony ridges connecting the neural spine to the front part of the vertebra, known as spinopresagapophyseal laminae, or SPPLs. These features were particularly well developed in Patagotitan and used to group loncosaurs together with Notocolossus, setting them apart from other titanosaurs. Interestingly, this grouping of colossal dinosaurs corresponded with a dramatic increase in body size. While earlier titanosaurs typically weighed around 20 tons, or 22 short tons, members of the Loncosauria soared to around 60 tons, or 66 short tons. Other massive titanosaur species like Dreadnoughtus and Alamosaurus also grew very large, but their size increase was much less extreme. Beyond this, Logoncosaurs, along with Notocolossus and Bonitosaura, formed a sister group to another group called the Rinconsaria. Unlike previous studies, Carbolito and his team concluded that Loncosauria was not part of the Lithostrocha, but rather a separate lineage within Eutitanosauria, which itself is part of the larger Titanosauria. Over the years, the relationships between different titanosaurs have been notoriously tricky and inconsistent, with various studies producing different family trees. Despite this, Patagotitan has consistently been found closely linked with Argentinosaurus and Puertosaurus, often identified as either the closest relative to one another. In the year 2018, Bernardo Gonzalez Riga and his colleagues discovered that Patagotitan, Puertosaurus, and Notocolossus formed a polytomy, a kind of three-way tie, with Argentinosaurus being nearest to this group. Their analysis differed slightly from Carbolito's because they placed Loncosauria within Lithostrocha. A year later, in 2019, Gonzalez Riga's team found the same arrangement and gave the broader grouping of Loncosauria and Rinconsaria a new name, Colossosauria. That same year, Philip Mannion and his team also studied these relationships, placing Patagotitan, Puertosaurus, and Notocolossus in a polytomy alongside other giant titanosaurs like Futaloincosaurus, Mendozasaurus, and Argentinosaurus, with the exact positions shifting depending on which titanosaurs were included or excluded in the study. In 2020, Carbolito and colleagues once again found Patagotitan paired with Argentinosaurus, forming a polytomy with Puertosaurus and Drusilla while placing Logoncosauria outside Lithostrocha. Similar arrangements were confirmed in later studies, including those by Federico Agnolin in 2023, Otero in 2021, and Pablo Galina also in 2021, with slight variations involving Ninjatitan. In 2023, Agustin Perez Moreno and colleagues updated Galina's analysis, finding Ninjatitan closer to Rinconsaria. Thanks to its remarkable preservation, Carbolito and his team, in the year 2022, found that Patagotitan is one of the most phylogenetically stable titanosaurs, meaning its place in the dinosaur family tree is very secure. They measured this stability with a recovery index of 62%, showing that it remained in the same position in over half of the analyses. They also noted that the uncertainty about whether Loncosauria belonged inside Lithostrotia mostly came from how Lithostrotia was defined, since it relied on the unstable dinosaur Malawisaurus. To resolve this, they suggested dividing Eutatanosauria into two main branches, Saltasauroidea and Colossosauria, with Colossosauria defined as the group including Patagotitan, but not the smaller Saltasaurus. This refined classification focused only on the most stable giant titanosaurs. Patagotitan roamed a forested landscape during its time. At a site about 200 meters away from where its fossils were found, paleontologists uncovered a treasure trove of plant fossils. These included fern pinnules, leaves, cones, and fossilized wood from conifers, as well as leaves, flowers, and wood from flowering plants or angiosperms. Conifers dominated this ancient forest, while flowering trees were relatively rare. Among these discoveries, scientists identified a new genus of cypress-like tree called Ostrocupressinoxylon, reminiscent of modern Fitzroya and Pilgerodendron, which likely grew to about 15 meters tall. Another discovery included a new species of angiosperm wood, Carlquistoxylon australe, named in 2018. The fossils of Patagotitan were found in fine-grained sandstone and siltstone that contained volcanic ash, indicating a calm, low-energy water environment on a floodplain. The floods that occasionally swept through this area were gentle, probably too weak to carry away the enormous bodies, suggesting that the dinosaurs were preserved exactly where they had died. Other creatures sharing this ancient environment included giant predatory dinosaurs like Tyrannotitan and Geniodectes, a crocodiliform named Barsinosuchus, and the turtle Chubutamis, painting a vivid picture of a dynamic ecosystem full of towering giants, lurking hunters, and armored reptiles. Dreadnoughtus is a type of giant titanosaurian sauropod dinosaur, known from a single species called Dreadnoughtus shrani. Its fossils come from rocks of the Cerro Fortaleza Formation in Santa Cruz Province, Argentina, which date back to the very end of the Cretaceous period, around 76 million to 70 million years ago. This dinosaur ranks among the largest land animals ever discovered with reasonably complete skeletons. The holotype, or main specimen, which was not fully grown, measured about 26 meters in length, nearly 85 feet, and may have weighed as much as 48 to 49 metric tons, roughly 53 to 54 short tons. Compared to other enormous titanosaurs, Dreadnoughtus is known for more complete skeletons, giving paleontologists a rare glimpse into the anatomy of these massive creatures. The dinosaur was discovered in two partial skeletons by the American paleontologist Kenneth Lacavara in the year 2005. Lacavara explained that he chose the name Dreadnoughtus, meaning fears nothing, because he wanted to highlight the strength and resilience of giant herbivorous dinosaurs. The name was also inspired by the early 20th century battleship called the Dreadnought, famous for its massive size and firepower, which made older, smaller battleships seem weak by comparison. The excavation of Dreadnoughtus was a massive undertaking. Its enormous bones were located in a remote area of Patagonia, and it took Lacavara and his team 4 austral summers, working with ropes, mules, and many helpers, to carefully remove the fossils from the ground and prepare them for transport. In the year 2009, the fossils were shipped by ocean freighter to Philadelphia, where scientists at Drexel University, the Academy of Natural Sciences of Drexel University, and the Carnegie Museum of Natural History carefully cleaned, studied, and analyzed them. In March of the year 2015, the fossils were returned to their permanent home at the Museo Padre Molina in Rio Gallegos, Argentina. Modern technology played a key role in studying these massive bones. Both skeletons were scanned using a 3-dimensional laser scanner, and the digital scans were arranged using software to create a virtual skeleton in 3 dimensions. This allowed the fossils to be studied safely without handling the heavy bones, and enabled scientists to collaborate with colleagues around the world. The holotype skeleton, MPM-PV 1156, is quite extensive. It includes fragments of the jaw and a tooth, several neck and back vertebrae, ribs, the sacrum, 32 tail vertebrae, and 18 tail bones known as hymal arches, much of the left shoulder and forelimb, excluding the front foot, both chest bones, all parts of the pelvis, the left hind leg, missing the foot and right shin bone, 2 foot bones, and 1 claw. The second specimen, called the paratype, MPMPV 3546, belonged to a slightly smaller individual found in the same location and included parts of the neck, back, and tail, a nearly complete pelvis, and the left thigh bone. The researchers who named Dreadnoughtus explained that the genus name honors both the incredible size of the dinosaur, making it almost untouchable to predators, and Argentina itself, referencing 2 early 20th century Argentine battleships, Rivadavia and Moreno. The species name, Shrani, was chosen to recognize the American supporter Adam Schran, who funded the project. Estimating the weight of Dreadnoughtus has been a challenge. Using a mathematical formula based on the circumference of its limb bones, the original research team concluded the dinosaur might have weighed around 59 metric tons, more than 8.5 times heavier than a male African elephant, and even heavier than a Boeing 737-900 airliner. However, these numbers were quickly debated. Some scientists suggested that more realistic volumetric models put its weight between 30 and 40 metric tons, with a few estimates as low as 26 metric tons. Other studies considered the possibility that the original formulas might overestimate weight for such enormous animals, especially because the holotype was not fully grown. A more thorough review in June of the year 2015 used digital 3-dimensional models to include muscles, skin, and even space for the respiratory system. This study suggested that Dreadnoughtus likely weighed between 22 and 38 metric tons, a range much lower than the original estimate. Debates continued, but by the year 2019, Gregory S. Paul estimated the holotype at about 31 metric tons, with the possibility that it might have been slightly heavier. Later studies refined these estimates further, suggesting an immature Dreadnoughtus may have weighed around 48 metric tons, showing that even younger individuals of this species were immense and awe-inspiring. The discovery of Dreadnoughtus shrani has given paleontologists a remarkable window into the lives of the largest titanosaurian sauropods, especially revealing new details about their enormous limbs, as well as their shoulder and hip structures. Most of the bones of Dreadnoughtus are astonishingly well preserved, with very little distortion. The limb bones, in particular, remain nearly perfect, allowing scientists to see fine details, such as the exact points where muscles once attached. One striking feature of this dinosaur is its exceptionally long neck, which stretched to almost half the total length of its body, giving it a distinctive and elegant silhouette. By carefully measuring the bones that have been found, researchers estimate that the only known individual of Dreadnoughtus shrani reached a length of about 26 meters, which is roughly 85 feet, and stood about the height of 2 stories. Its shoulder blade, or scapula, was a staggering 1 meter and 74 centimeters long, making it longer than that of any other titanosaur ever discovered. The top bone of the pelvis, called the ilium, was also enormous, measuring 1 meter and 31 centimeters from end to end. Its forearm was longer than those of any other titanosaur, surpassed only by the elongated forearms of Brachiosaurids, dinosaurs that had a more inclined body posture. Only Paralidotin preserved a longer upper arm bone, or humerus. While different titanosaur species had slightly varied body proportions, these measurements clearly showcase the immense size and power of Dreadnoughtus shrani. The total weight of this dinosaur is estimated to have been around 48 to 49 metric tons, which is approximately 53 to 54 short tons. Determining the completeness of a sauropod skeleton can be tricky. Many sauropod fossils are found without skulls, so scientists often focus on postcranial completeness, which considers all bones except the skull. Completeness can also be measured by counting the total number of bones, or by assessing the variety of different bones present. For understanding the anatomy of a dinosaur, the diversity of bones is generally more important than the sheer number. In the year 2022, paleontologist Schroeder and her colleagues made an extraordinary discovery. They found traces of soft tissues and collagen in the holotype specimen of Dreadnoughtus. They suggested that the individual may have been rapidly buried soon after death, which would explain why this particular skeleton is more complete than almost all other titanosaurs. Like all titanosaurs, Dreadnoughtus had a stance called wide-gauge posture, meaning its legs were spread further apart than the midline of its body. More advanced titanosaurs tended to have even wider stances. Dreadnoughtus shrani clearly had a wide-gauge stance, although not as extreme as that of Saltosaurids. Its thigh bones, or femurs, had lower ends that were perpendicular rather than slanted, and the femur heads were not turned inward like in Saltosaurids. This supports the idea that Dreadnoughtus was not a member of the Saltosaurid family. Its broad breastbones also created a wide shoulder and chest, giving it a massive, solid appearance. Paleontologist Kenneth Lacavara once compared its gait to that of an imperial walker from science fiction, highlighting its steady, lumbering yet powerful movement. Despite its forelimbs being longer than any other known titanosaur, they were not much longer than the hind limbs. This suggests that Dreadnoughtus likely held its neck more horizontally, unlike the angled neck posture of Brachiosaurus. Its tail also had several unique features. The first tail vertebra had a ridge along its underside called a keel. In the first third of the tail, the neural spines, which project upwards from the vertebrae, were divided into many cavities linked to air sacs, part of the dinosaur's respiratory system. Distinct ridges connected the front and back edges of these spines to the points where the vertebrae articulated. In the middle section of the tail, the vertebrae had triangular projections reaching towards the previous vertebra. Just as in modern reptiles with tails, like crocodiles, Dreadnoughtus had bones beneath the tail vertebrae called chevrons or hemal arches. These Y-shaped bones were broad at the bottom, providing strong attachment points for tail muscles. The shoulder and forelimb bones of Dreadnoughtus also had distinctive characteristics. The scapular blade had an oblique ridge running across its inner surface, from near the top end to the base. Each end of the radius, one of the forearm bones, was unique. The top end had a concave notch on its back surface, and the bottom end was almost square rather than wide and flattened. From a phylogenetic perspective, Dreadnoughtus shrani appears to be a derived basal titanosaur, meaning it had some advanced features, but was not quite part of the Lithostrosian group. Lacavara and colleagues noted that the combination of both primitive and advanced features in its skeleton, together with the currently unstable understanding of titanosaur relationships, means its exact place in the family tree could change with future research. Later studies on its limbs suggested that Dreadnoughtus shares many traits with Lithostrosians, particularly Aeolosaurus and Gondwanatitan, hinting it may be closely related to that group. Future analyses are expected to explore these relationships further. The holotype individual was not fully grown when it died. Bone tissue analysis of the humerus revealed no external fundamental system, a feature only found in fully mature vertebrates, and showed abundant fast-growing bone tissue. This indicates that the dinosaur was still growing at the time of its death. The site where the bones were found shows evidence of rapid burial in a flood caused by a sudden break in a river levee, creating a liquefied deposit that entombed the two Dreadnoughtus individuals. This quick and deep burial explains why the holotype specimen is so remarkably complete. Among the bones, scientists also found many small theropod teeth, likely the remains of scavengers such as megaraptorans, possibly Orcoraptor, which fed on the carcasses after the flood. Supersaurus was a type of enormous, long-necked, long-tailed dinosaur called a diplodocid sauropod, which roamed the lands of what is now North America during the late Jurassic period. The first species, Supersaurus viviani, was discovered in the year 1972 by Vivian Jones, a resident of Delta, Colorado. The fossils came from the middle layers of the Morrison Formation in Colorado, specifically from a section known as the Brushy Basin Member, which dates back roughly 153 to 145 million years ago. Supersaurus is famous for being one of the longest dinosaurs ever found. Of the three known specimens, their lengths ranged from 33 to 40 meters, which is about 108 to 131 feet, and the largest individual might have even surpassed 40 meters, roughly 130 feet. Scientists estimate that the body mass of the Wyoming Dinosaur Center and Brigham Young University specimens was between 35 and 44 metric tons, or 39 to 49 short tons. There is also evidence of a possible second species, known as Supersaurus laurinensis, sometimes called Dinosaurus, discovered in Portugal, which lived around the same time. Supersaurus fossils are found in what paleontologists call stratigraphic zone 5 of the Morrison Formation, corresponding to the Tithonian stage of the late Jurassic. The very first remains of Supersaurus were uncovered in the Dry Mesa Quarry in 1972. These initial finds were sparse, consisting mainly of parts of the shoulder, a portion of the hip called the ischium, and several tail vertebrae. The dinosaur was formally described by paleontologist James A. Jensen, who designated a particular shoulder bone, known as a scapulocoracoid, labeled BYU 9025, originally BYU 5500, as the type specimen for the species. This shoulder bone, if stood upright, would have reached about 2.4 meters in height, almost 8 feet. Jensen informally referred to the dinosaur as Supersaurus as early as 1973, but the official description and naming were not published until 1985. At one point, researcher Jack McIntosh suggested that the BYU Supersaurus fossils might represent a very large species of Brachiosaurus, but later evidence supported the idea that Supersaurus was indeed a distinct genus. A far more complete specimen was discovered in Converse County, Wyoming, in 1986 by two hikers, Brandon Flyer and Bart Lesko, who reported the find to the landowners. This specimen, nicknamed Jimbo by the family who later purchased the land in 1996, was formally described and identified as Supersaurus in 2007. The bones preserved about 30% of the entire skeleton and are now kept at the Wyoming Dinosaur Center. Comparing this specimen to the earlier dry mesa quarry, finds helped paleontologists determine which bones truly belong to Supersaurus. This study suggested that some tail vertebrae and a forearm bone, called an ulna, might actually belong to a different diplodocid species. Interestingly, James Jensen, who had described the first Supersaurus fossils, also reported another gigantic sauropod, which he later called Ultrasaurus macintoschi, renamed Ultrasaurus macintoschi. However, it was eventually discovered that the backbone used as the type specimen for Ultrasaurus actually came from Supersaurus, likely belonging to the original 1972 find in the same quarry. As a result, Ultrasaurus was considered a junior synonym of Supersaurus, and its name was abandoned. Other bones found at the dry mesa quarry that were initially attributed to Ultrasaurus, such as a shoulder bone labeled BYU 9462, were later identified as belonging to Brachiosaurus, probably a large individual of Brachiosaurus altathorax. These bones represented a sizable, but not record-breaking dinosaur, slightly larger than the famous mounted Giraffitan bronchi in Berlin's Natural History Museum. Initially, scientists thought that the Supersaurus and Brachiosaurus bones came from a single gigantic dinosaur, which they estimated to be 25 to 30 meters long, roughly 82 to 98 feet, 8 meters high at the shoulder, about 26 feet, 15 meters tall in total, around 49 feet, and weighing perhaps 70 metric tons, or 77 short tons. Some early mass estimates even soared to 180 tons, placing it alongside the enormous blue whale and the famously controversial Brachiosaurus. The story of the naming of Ultrasaurus was equally tangled. Jensen had originally chosen the name Ultrasaurus, which gained media attention after a 1979 discovery. But for a dinosaur's name to become official, it must be published with a formal description. Before Jensen could do this in 1985, a paleontologist in South Korea named Kim Hong-mook used the name Ultrasaurus in 1983 to describe what he thought was a giant dinosaur. Kim's dinosaur was much smaller, but he misidentified a humerus as an ulna, leading him to believe it was enormous. Since Kim published first, his Ultrasaurus name retained priority, forcing Jensen to rename his discovery Ultrasaurus in 1991. Later, when it was realized that the bones referred to two already known species, the name Ultrasaurus became invalid and was recognized as a junior synonym of Supersaurus. Another diplodocid found near the original Supersaurus quarry, known from a backbone labeled BYU 5750, was named Distylosaurus edwini, but is now also considered a specimen of Supersaurus viviani, making Distylosaurus another junior synonym. Today, Supersaurus is recognized as one of the largest dinosaurs ever found with good fossil evidence and possibly the longest known. The Wyoming Dinosaur Center specimen reaches approximately 33 to 36 meters in length, 108 to 118 feet. The BYU specimen may have stretched up to 39 meters, 128 feet, and a third specimen could have exceeded 40 meters, 130 feet. The estimated body mass of the Wyoming Dinosaur Center and BYU specimens ranges from 35 to 44 metric tons, or 39 to 49 short tons. A study conducted in the year 2024 examined the famous Jimbo specimen of Supersaurus and concluded that it had reached full skeletal maturity at the time of its death, making it one of the oldest dinosaurs ever discovered. While the analysis produced a calculated age of 225 years, the researchers emphasized that such a number is extremely unlikely. Instead, this unusually high figure highlights the limits of the methods used to estimate the age of extraordinarily old dinosaurs. The same study also examined a Diplodocus hallorum that measured about 33 meters, or 108 feet in length. That dinosaur was found to be roughly 60 years old, which already places it among the oldest known dinosaurs. However, the researchers believed that Jimbo was even older, based on the extensive remodeling observed in its bones. In fact, the study suggested that Jimbo was so ancient that its exact age could not be reliably determined using the available techniques. Despite this uncertainty, the Jimbo specimen can reasonably be considered possibly the oldest dinosaur ever identified. The research also indicated that because Jimbo had reached skeletal maturity, the range of sizes seen in the three known Supersaurus specimens, ranging from 33 to 40 meters, or 108 to 131 feet, likely represents the typical size of an adult of this species. The earliest described Supersaurus fossils were single, isolated bones, but they already hinted at a truly massive diplodocid. Among these, a particularly large cervical vertebra, catalogued as BYU 9024, was discovered in the same quarry and was later attributed to Supersaurus. This vertebra measures approximately 1 meter and 38 centimeters, or 4.5 feet, making it the longest neck bone ever documented. At one point, paleontologists Mike Taylor and Matt Weddle reclassified this enormous vertebra as belonging to Brachiosaurus. However, researcher Brian Curtis later reassigned it back to Supersaurus after additional fossils provided supporting evidence. Michael Benton also agreed with this reclassification and estimated that the Supersaurus represented by BYU 9024 could have reached an astounding length of up to 50 meters, or 160 feet, which would make it the longest animal known to have ever walked the Earth. The more complete Supersaurus specimen reveals that in most aspects of its anatomy, it closely resembled Apatosaurus. However, it was more lightly built, with especially elongated neck vertebrae, giving it one of the longest necks ever recorded in any sauropod. Most studies of diplodocid relationships divide the family into two main groups: Diplodocini, which includes those diplodocids more closely related to Diplodocus than to Apatosaurus, and Apatosaurini, which includes those more closely related to Apatosaurus than to Diplodocus. Originally, Supersaurus was thought to be related to the long-necked Brachiosaurus, placing it in Diplodocinae. Yet, after the discovery of the more complete WDC-DMJ021 specimen, most later studies found that Supersaurus was actually a close relative of Apatosaurus, placing it in Apatosaurini. Still, some research challenged this view. A detailed study of diplodocoid relationships published by Whitlock in the year 2011 suggested that Apatosaurus itself occupies a basal position in the diplodocid family tree, while other supposed Apatosaurines, including Supersaurus, might actually be progressively more closely related to Diplodocus, placing them back in Diplodocini. In the year 2015, another study that analyzed diplodocids at the level of individual specimens found that Dinosaurus lawrenensis grouped closely with Supersaurus. This research proposed that Dinosaurus should actually be considered a new species of Supersaurus, leading to the new combination Supersaurus lawrenensis. Brachiosaurus is a type of sauropod dinosaur that lived in what is now North America during the late Jurassic period, roughly between 156 and 146 million years ago. This enormous creature was first described in the year 1903 by the American paleontologist Elmer S. Riggs. He based his description on fossils discovered in the valley of the Colorado River in western Colorado, United States. Riggs gave this dinosaur the scientific name Brachiosaurus altithorax. The first part of the name, Brachiosaurus, comes from Greek words meaning arm lizard, referring to its unusually long front legs, while the second part, altithorax, translates to deep chest, highlighting its wide, barrel-shaped body. Brachiosaurus was a true giant. It is estimated to have stretched between 18 and 22 meters in length, which is about 59 to 72 feet. The body mass of the type specimen, which was not fully grown, is thought to have ranged from 28 to 47 metric tons, or roughly 31 to 52 short tons. Like most sauropods, it had a very long neck, a relatively small head, and an overall massive body. But unlike its relatives, its front legs were longer than its back legs, giving it a sharply sloping body and a shorter tail in proportion to its size. Brachiosaurus is the species that gave its name to the family Brachiosauridae, which includes a few other large, long-necked dinosaurs. Interestingly, many of the popular images of Brachiosaurus that appear in books and movies are actually based on a related dinosaur called Giraffitan from Tanzania. Originally, Giraffitan was described as a species of Brachiosaurus in 1914 by German paleontologist Werner Janensch, but in 2009 it was recognized as a separate genus. Scientists have also named 3 other species of Brachiosaurus based on fossils from Africa and Europe, though 2 of these are now considered invalid, and the third has been reclassified into its own genus called Lusatitan. The original Brachiosaurus altithorax specimen remains the most complete known, and only a few other fossils are thought to belong to this genus, making it one of the rarer dinosaurs of the Morrison Formation. It was likely a high browser, feeding on leaves as high as 9 meters or 30 feet above the ground. Unlike some other sauropods, it was not built for rearing up on its hind legs. Early studies suggested that because of its massive size, Brachiosaurus might have been cold-blooded, needing enormous amounts of vegetation to survive. However, more recent research indicates it was likely warm-blooded. Its size and iconic shape have made it a favorite in popular culture, especially in the 1993 film Jurassic Park, where it became one of the most famous dinosaurs on screen. The type specimen of Brachiosaurus was found in the year 1900 in the Colorado River Valley near the town of Fruita, Colorado. This skeleton comes from rocks belonging to the Brushy Basin member of the Morrison Formation, which makes it around 154 to 153 million years old. Riggs and his team from the Field Columbian Museum in Chicago, now known as the Field Museum of Natural History, led the excavation. The discovery came about thanks to Riggs's correspondence with Stanton Merrill Bradbury, a dentist and amateur fossil collector in nearby Grand Junction. In the spring of 1899, Riggs had written letters to town officials across western Colorado, asking about possible trails that might lead to fossil-rich areas in northeastern Utah. To his surprise, Bradbury informed him that dinosaur bones had been collected near Grand Junction for more than a decade, since 1885. Although Riggs was initially skeptical, the museum's geology curator, Oliver Cummings Farrington, was eager to secure a large sauropod skeleton for the museum and convinced management to invest $500 in an expedition. Riggs and his team arrived on June 20, 1900, and set up camp at the abandoned goat ranch. While exploring on horseback, field assistant Harold William Menke found a humerus bone on July 4th, exclaiming that it was the biggest thing yet. Riggs initially thought it belonged to a Brontosaurus and focused on a more promising Morosaurus skeleton in Quarry 12. However, on July 26th, he returned to the humerus in Quarry 13, realizing its enormous size and understanding that he had discovered what might be the largest land animal ever. The excavation site, now called Riggs Quarry 13 or Riggs Hill, is marked today by a plaque. Some additional Brachiosaurus bones have been found there, although other fossils on the hill have suffered vandalism over the years. During the dig, Riggs misidentified the humerus as a deformed femur because of its unusual size. Only after careful laboratory preparation did it become clear that it was indeed a humerus. The excavation drew large crowds, which delayed work and required Menke to guard the bones from potential theft. By August 17th, the last bone had been secured in plaster. The team then spent 10 more days prospecting before returning to Grand Junction. It took 5 days to transport all the fossils to the railway station, and another week to pack them into 38 crates, weighing a total of 5,700 kilograms, or 12,500 pounds. Riggs left for Chicago on September 10th, arriving on the 15th, with the railroad companies generously allowing free passage for both passengers and cargo as a public relations gesture. The main Brachiosaurus skeleton, known as the holotype, includes several important bones from the right side of the body: the humerus, which is the upper arm bone, the femur, or thigh bone, the ilium, part of the hip, the coracoid, a shoulder bone, the sacrum, which is a group of fused vertebrae in the hip region, the last 7 vertebrae of the back, 2 vertebrae from the tail, and several ribs. Initially, Elmer S. Riggs, who described the find, thought the coracoid came from the left side of the body, but later studies showed it actually belonged to the right side. When the skeleton was first discovered, the lower part of the humerus, the underside of the sacrum, the ilium, and the preserved tail vertebrae had been exposed to the air and were partially damaged by weathering. The vertebrae were only slightly moved from their natural positions, and they were found upside down. The ribs, humerus, and coracoid, however, had shifted to the left side of the spine, suggesting they had been moved by flowing water. Evidence for this also comes from a lone ilium of a diplodocus that appears to have drifted nearby, and from changes in the surrounding rocks. While the specimen itself was buried in fine clay, which forms under calm water conditions, a thick layer of coarser rock, including pebbles at the bottom and sandstone above, cut through the specimen at the 7th vertebra in front of the sacrum, showing that stronger currents had once swept through the area. Based on these clues, Riggs suggested in 1904 that the missing front portion of the skeleton had been washed away by water, while the back portion was already covered in sediment and so remained preserved. Riggs first published a brief report about this discovery in 1901. He noted the humerus was unusually long compared to the femur, giving the dinosaur a body shape somewhat like a giraffe, with long front limbs and a relatively small tail. However, he did not yet give the dinosaur a name. 2 years later, in 1903, he officially named the species Brachiosaurus altithorax. The genus name comes from the Greek words brachion, meaning arm, and sauros, meaning lizard, chosen because the front limbs were exceptionally long for a sauropod. The species name, altithorax, combines the Latin word altus, meaning deep, with the Greek thorax, meaning chest or breastplate, referring to its unusually wide and deep chest cavity. At the time, Latin thorax had become the common scientific term for the body's chest. The titles of Riggs's 1901 and 1903 papers highlighted that this skeleton represented the largest known dinosaur. Riggs followed this with a much more detailed study published in 1904. Work on preparing the holotype began in the fall of 1900, shortly after Riggs collected it for the Field Museum. The first bones to be cleaned and prepared were the limbs. In the winter of 1904, the badly weathered vertebrae of the back and hip were carefully prepared by James B. Abbott and C.T. Klein. As each bone was finished, it was placed in a glass display case in Hall 35 of the Fine Arts Palace at the World's Columbian Exposition, the Field Museum's original location. By 1908, all the bones were still on display in Hall 35 when the Field Museum revealed its newly mounted Apatosaurus, the very specimen Riggs had found in Quarry 12 and identified as a Brontosaurus. Because only about 20% of the Brachiosaurus skeleton had been recovered, no full mount was attempted at the time. In 1993, the holotype bones were molded and cast in plastic. The missing bones were sculpted based on a related species, Brachiosaurus bronchi, today known as Giraffitan, held at the Museum für Naturkunde in Berlin. This reconstructed skeleton was mounted and displayed in 1994 at the north end of Stanley Field Hall, the main exhibition space of the Field Museum's current building. The original bones of the holotype were placed in 2 large glass cases at either end of the mounted cast. The mount remained there until 1999, when it was moved to the B concourse of United Airlines Terminal 1 at O'Hare International Airport to make space for the museum's newly acquired Tyrannosaurus, nicknamed Sue. At the same time, a second outdoor cast of the skeleton was created and placed on the museum's northwest terrace, remaining there until 2022. Another outdoor cast was sent to Disney's Animal Kingdom to serve as a centerpiece at the entrance to the Dino Land USA area. This cast, called the Olden Gate Bridge, connects the 2 halves of the fossil quarry-themed boneyard play area, welcoming visitors as they explore the dinosaur-themed attractions. Discoveries of Brachiosaurus fossils in North America have been relatively rare, often limited to just a few scattered bones. To this day, paleontologists can only confidently assign certain remains to this genus when they directly match parts of the original type specimen, known as the holotype. Any fossils from the skull, neck, front portion of the back, or the lower limbs and feet remain uncertain and must be treated cautiously. Despite this, bones have been described from Colorado, Oklahoma, Utah, and Wyoming, and several other sites have mentioned fossils that have not yet been formally described. In the year 1883, a farmer named Marshall Parker Felch, who worked as a fossil collector for the famous American paleontologist Othniel Charles Marsh, reported finding a sauropod skull at Felch Quarry 1 near Garden Park in Colorado. The skull was embedded in yellowish-white sandstone and was found close to a cervical vertebra that measured about 1 meter in length, although this vertebra was unfortunately destroyed during an attempt to extract it. The skull was catalogued as YPM 1986 and sent to Marsh at the Peabody Museum of Natural History. Marsh included it in his 1891 skeletal reconstruction of Brontosaurus, likely because Felch had initially thought it belonged to that dinosaur. The Felch Quarry skull itself is fairly complete. It includes the main skull, both upper jaw bones called maxillae, the right postorbital bone, part of the left maxilla, the left squamosal, the lower jaw bones called dentaries, and a possible fragment of the pterygoid. The preparation of the skull was rough, which caused some damage. Felch also collected several other bones from the body, including part of a neck vertebra and a forelimb fragment. After Marsh passed away, most of Felch's specimens, including this skull, were sent to the National Museum of Natural History in 1899, where the skull received a new catalog number, USNM 5730. In 1975, American paleontologists Jack McIntosh and David Berman revisited the historical question of whether Marsh had incorrectly assigned the Felch Quarry skull to Brontosaurus, which at that time was considered just another name for Apatosaurus. They determined that the skull was generally similar to Camarasaurus, a different sauropod, while the nearby vertebra probably belonged to Brachiosaurus. They concluded that if Marsh had not arbitrarily assigned the skull to Brontosaurus, paleontologists would have recognized much earlier that the real skulls of Brontosaurus and Apatosaurus were more similar to Diplodocus. Later, McIntosh tentatively suggested that the Felch Quarry skull belonged to Brachiosaurus and drew the attention of American paleontologists Kenneth Carpenter and Virginia Tidwell to it. They transported the skull to the Denver Museum of Natural History, where it underwent further preparation and reconstruction using casts of individual bones. Missing parts were modeled based on the skulls of Giraffitan and Camarasaurus as guides. In 1998, Carpenter and Tidwell formally described the Felch Quarry skull and assigned it to Brachiosaurus sp, meaning its exact species was uncertain. They could not determine if it belonged specifically to Brachiosaurus altithorax, since there were no overlapping bones with the holotype. They based this classification on its similarity to the skull of Brachiosaurus branchi, later renamed Giraffitan. Then, in 2019, American paleontologists Michael D. Demick and Matthew T. Carano re-examined the skull. They had it further prepared and CT scanned, consulting historical illustrations that showed its earlier condition. They concluded that a large quadrate bone and a tooth previously thought to belong to the skull actually did not. The quadrate was too large to fit properly and had been found several meters away, while the tooth was much bigger than those in the jaw and more consistent with Camarasaurus, a species already known from the quarry. Demick and Carano found it more reasonable to assign the skull to B. altithorax itself, as there is no evidence of other brachiosaur species in the Morrison Formation, and adding these and other elements to a phylogenetic analysis did not change the dinosaur's position in the evolutionary tree. Another notable specimen is a shoulder blade with a coracoid from Dry Mesa Quarry, Colorado, which was involved in debates about the identities of Supersaurus and Ultrasauros during the 1980s and 90s. In 1985, James A. Jensen described disarticulated sauropod bones from the quarry as belonging to several enormous dinosaurs, introducing the new genera Supersaurus and Ultrasaurus. The latter name was soon changed to Ultrasauros because it had already been used for another dinosaur. Later studies showed that most of the so-called Ultrasaur bones actually belonged to Supersaurus, except the shoulder blade, catalogued as BYU 9462, which was reassigned to Brachiosaurus sps by Brian Curtis and colleagues in 1996. In 2009, Michael P. Taylor concluded that the shoulder blade could not be confidently referred to B. altithorax. The Dry Mesa shoulder and coracoid suggested that the dinosaur was smaller than the original Brachiosaurus holotype described by Elmer S. Riggs. Several other fossils were briefly described by Jensen in 1987. One of these, the humerus USNM 21903, was discovered around 1943 by uranium prospectors Vivian and Daniel Jones at Potter Creek Quarry in western Colorado. It was donated to the Smithsonian Institution. Originally, this humerus was part of a poorly preserved partial skeleton that had not been collected in full. According to Taylor in 2009, despite its impressive length of about 2 meters and 13 centimeters, it is not certain that this bone belonged to Brachiosaurus. Jensen also excavated disarticulated bones at Potter Creek in 1971 and 1975, catalogued as BYU 4744, which included a mid-back vertebra, part of a left hip, a left radius, and a right-hand bone. Taylor later concluded that these could be confidently assigned to B. altithorax, based on overlap with the holotype. Jensen also mentioned a find near Jensen, Utah, including a rib measuring 2 meters and 75 centimeters in length, a front neck vertebra, and parts of a shoulder blade and coracoid, although no full description was published. In 2001, Curtis and Statman assigned 2 articulated back vertebrae from Dry Mesa Quarry, catalogued as BYU 13023, to Brachiosaurus. Taylor noted in 2009 that these vertebrae were shorter than those of the B. altithorax holotype, but otherwise similar. In 2012, Jose Carbolito and colleagues reported a nearly complete postcranial skeleton of a small juvenile, approximately 2 meters in length, nicknamed Tony, and catalogued as SMA 0009. This specimen came from the Morrison Formation in the Bighorn Basin of north-central Wyoming. Originally thought to be a diplodocid, it was later reclassified as a brachiosaurid, probably belonging to B. altithorax. In 2018, the largest sauropod foot ever discovered was reported from the Black Hills of Weston County, Wyoming. The femur was missing, but comparisons suggested it was about 2% longer than that of the B. altithorax holotype. Although it might belong to Brachiosaurus, it was cautiously classified as an indeterminate brachiosaurid. In 2019, Diemick and Carano questioned the assignments of both Tony and the enormous foot, suggesting that earlier interpretations of B. altithorax's unique features or the damaged state of the bones may have led to incorrect conclusions. They emphasized that further study is needed, though they noted general similarities to other brachiosaurids such as Sonorosaurus and Giraffitan. Between the years 1909 and 1912, large and ambitious paleontological expeditions took place in German East Africa, where explorers uncovered a remarkable collection of brachiosaurid dinosaur remains from the Tendaguru Formation. In the year 1914, the German paleontologist Werner Janisch carefully examined these fossils and compared them with Brachiosaurus altithorax, a species known from North America. He noted both the similarities and differences, and concluded that these African fossils could indeed be placed within the genus Brachiosaurus. From this rich collection, Janisch described 2 species, Brachiosaurus branchi, which was larger and more complete, and Brachiosaurus frasi, which was smaller and much less well known. Over the following decades, Janisch continued to study these fossils in more detail. In the years 1929, 1950, and 1961, he published additional papers comparing the African species to B. altithorax, identifying 13 characteristics shared between Brachiosaurus branchi, which he now considered to include B. frasi, and B. altithorax. Many years later, in 2009, paleontologist Michael Taylor revisited these comparisons and concluded that only 4 of those 13 traits were truly valid for distinguishing the genus, while 6 applied more broadly to other related groups, and the rest were either hard to evaluate or came from fossils not confidently assignable to Brachiosaurus. The Museum für Naturkunde in Berlin held a vast amount of material attributed to B. branchi. Unfortunately, much of it was destroyed during the devastation of the Second World War. Some additional material had been sent to other institutions in Germany, but portions of those collections were also lost during the war. Meanwhile, the British Museum of Natural History carried out its own expedition to Tendaguru, collecting further remains, including a nearly complete skeleton discovered by F. W. H. Migiod in 1930. Today, This specimen is thought to represent a new, as yet undescribed species. Janinch's original description of Brachiosaurus branchi was based on a specimen he called Skeleton S from Tendaguru. Later, he realized that this skeleton actually consisted of two partial individuals, which he labeled SY and S2. Initially, he did not officially designate either as the primary type specimen, but in 1935 he selected S1 as the lectotype. Unaware of this, Taylor in 2009 proposed using the larger and more complete S2 as the lectotype. This skeleton includes many important bones, such as several back vertebrae, the left shoulder blade, both coracoids, the breastbone, both upper arm bones, both forearm bones, a right hand, a partial left hand, both hip bones, and the right thigh, shin, and calf bones. Taylor later realized in 2011 that Janinch had indeed already designated S1 as the lectotype decades earlier. In 1988, the paleontologist Gregory S. Paul published a new reconstruction of Brachiosaurus branchi. He emphasized differences in body proportions between this African species and B. altithorax. Most notably, Paul observed that the vertebrae of the trunk were much more uniform in length in the African material, while in B. altithorax they varied widely. Paul also noted that the limbs and girdle bones were very similar between the two species, leading him to suggest that the differences might justify separation only at the subgenus level rather than full genera. He proposed naming them Brachiosaurus, Brachiosaurus, altithorax, and Brachiosaurus, Giraffitan, branchi. A few years later, in 1991, George Olszewski elevated Giraffitan to a full genus, emphasizing differences in vertebral structure. However, between 1991 and 2009, most researchers largely ignored the name Giraffitan. In 2009, Taylor conducted a comprehensive study of all the known material, including limb and shoulder bones. He identified 26 distinct skeletal differences between B. altithorax and the African fossils, more differences than exist between the well-known genera Diplodocus and Barosaurus. Based on these differences, he argued that the African material deserved its own genus, which he called Giraffitan branchi. Among the most noticeable differences between the two genera are their overall body shapes. Brachiosaurus had a back vertebral column that was approximately 23% longer and a tail that was about 20 to 25% longer and taller than that of Giraffitan. While paleontologist Daniel Chure rejected this distinction in 2010, most studies since 2012 have accepted the name Giraffitan. Brachiosaurid fossils were also found outside Africa. In 1947, at Atalaia in Portugal, remains were uncovered in rock layers dating to the Tithonian stage of the late Jurassic. In 1957, Albert Félix de Lapparent and Georges Zbyszewski named them Brachiosaurus atalaiensis. Later, the assignment of this species to Brachiosaurus was questioned, and by 2004, it was considered an unnamed brachiosaurid genus. Before this publication, in 2003, Miguel Teles Antunes and Octavio Mateos placed the species into its own genus, Lusotitan. They selected a partial postcranial skeleton as the lectotype, which included 28 vertebrae, chevrons, ribs, a possible shoulder blade, upper arm and forearm bones, a partial left pelvis, lower leg bones, and part of the right ankle. Features such as the low neural spines, the prominent attachment crest on the humerus, the long, slender humerus, and the upward-tilted ilium confirmed that Lusotitan was indeed a brachiosaurid, a conclusion supported by later studies including one in 2013. In 1958, the French petroleum geologist F. Nougared reported fragmentary brachiosaurid remains from eastern Algeria in the Sahara Desert. Based on these discoveries, Albert Félix de Lapparent described a new species, Brachiosaurus nougaredi, in 1960. He placed the fossils in late Jurassic-aged rocks, known as the Tauretine series, partly because he assumed Brachiosaurus was present there. More recent studies, however, place these rocks in the Albian stage of the late early Cretaceous, making them significantly younger than originally thought. The type material for B. nougaredi, which was moved to Paris, consisted of a sacrum weathered at the desert surface and some of the left metacarpals and finger bones. Other bones, including parts of the forearm, wrist, a right shin bone, and fragments possibly from the feet, were found at the site but not collected. By 2004, this species was considered a distinct, unnamed brachiosaurid genus. In 2013, a study by Philip D. Mannion and colleagues suggested that the remains may belong to more than one species, since they were found far apart. The metacarpals appeared to belong to an indeterminate titanosaury form, while the sacrum, originally estimated in 1960 to be 1 meter and 30 centimeters long, compared to 91 centimeters for B. altithorax, was reported lost. This sacrum, if complete, would have been larger than that of any other sauropod except Argentinosaurus and Apatosaurus. Only 4 out of 5 sacral vertebrae survive, and until it is rediscovered, it remains provisionally classified as an indeterminate sauropod. Most of what scientists believe about the size of Brachiosaurus altithorax comes from comparisons with its close relative Giraffitan, which was once thought to be another species of Brachiosaurus, called Brachiosaurus branchi. Giraffitan is known from far more complete skeletons than Brachiosaurus, which makes it a useful guide. Both of these enormous creatures are the largest known brachiosaurids for which relatively extensive remains have been found. However, there is some uncertainty about the North American Brachiosaurus because the type specimen, the one used to define the species and the most complete skeleton discovered, seems to have been a subadult. This is suggested by the fact that the coracoid, a bone in the shoulder girdle that forms part of the shoulder joint, had not yet fully fused with the scapula or shoulder blade. Over the years, scientists have estimated the weight of this main Brachiosaurus specimen to be anywhere from about 28.3 to 46.9 metric tons, which is roughly 31.2 to 51.7 short tons. Later, some researchers proposed that it could have weighed as much as 56 to 58 metric tons, or 62 to 64 short tons, though these higher estimates are questioned because the calculations are very imprecise. Its total length has been estimated at anywhere between 20 and 22 meters, which is approximately 66 to 72 feet, while other studies suggest it may have been slightly shorter, around 18 meters or 59 feet. Its height, measured to the top of the shoulders, has been estimated at about 9 meters and 3/4 of a foot, or up to 12 to 13 meters, which is roughly 39 to 43 feet. The limb bones of Giraffitan's most complete skeleton are very similar in size to those of the Brachiosaurus-type specimen. Yet Giraffitan was probably lighter than Brachiosaurus because of subtle differences in body proportions. When scientists estimated the weights of both genera, they came up with numbers for Giraffitan ranging from about 23.3 to 39.5 metric tons, which is roughly 25.7 to 43.5 short tons, with other estimates falling around 31.5 to 34 metric tons, or 34.7 to 37.5 short tons. Even the largest known Giraffitan skeleton may not represent the maximum size for the genus, as another fibula, a lower leg bone, is 13% longer. Like all sauropod dinosaurs, Brachiosaurus walked on all 4 legs, with a small skull perched at the end of an extremely long neck. Its trunk was massive and had a high, rounded cross-section, while its long, muscular tail and column-like, slender limbs helped support its enormous bulk. Large air sacs connected to the lungs extended into the vertebrae and ribs, hollowing out parts of the bones and making the body lighter overall. The neck of the type specimen is missing, but judging by the closely related Giraffitan, it would have been exceptionally long even for a sauropod, made up of 13 elongated neck vertebrae. The neck likely had a gentle S-shaped curve, with the lower and upper sections slightly bent, and a straight middle portion. Brachiosaurus probably shared with Giraffitan the long, overlapping neck ribs that ran along the underside of the neck. These ribs were anchored to muscles near the trunk, but could move the distant parts of the neck, keeping the far end light and flexible. Both Brachiosaurus and Giraffitan probably had a small hump on the shoulders between the 3rd and 5th dorsal vertebrae, where the sideways and upward-pointing projections of the vertebrae were longer, providing extra attachment points for neck muscles. The rib cage of Brachiosaurus was particularly deep compared to other sauropods. Although its upper arm bone and thigh bone were roughly the same length, the forelimbs overall were longer than the hind limbs, thanks to an elongated forearm and hand bones. This created a sloping trunk, with the shoulders much higher than the hips, so that the neck rose steeply from the body. Its overall shape has often been compared to that of a giraffe. In contrast, most other sauropods, including the long-necked diplodocoids living at the same time, had forelimbs shorter than their hind limbs. Brachiosaurus also differed from Giraffitan in other ways. Its trunk was about 25 to 30% longer, meaning the dorsal vertebral column exceeded the length of the upper arm bone. Only one complete tail vertebra has been found, but its size suggests the tail was larger than that of Giraffitan, with the vertebra's broadened neural spine providing more space for ligament attachment, indicating the tail may have been 20 to 25% longer. Earlier, in 1988, paleontologist Gregory S. Paul proposed that Brachiosaurus had a shorter neck than Giraffitan. However, in 2009, paleontologist Mike P. Taylor noted that two cervical vertebrae likely belonging to Brachiosaurus had proportions identical to those of Giraffitan, suggesting a similar neck length. Unlike Giraffitan, which held its forelimbs almost vertically, Brachiosaurus seems to have had slightly splayed arms, based on the orientation of the coracoid joint surfaces. Its upper arm bone was thicker than that of Giraffitan, while the thigh bone had similar proportions. This could mean that Brachiosaurus's forelimbs bore more of its massive body weight than in Giraffitan. Although the back portion of Brachiosaurus's vertebral column is incomplete, scientists believe it had 12 dorsal vertebrae, inferred from another unnamed brachiosaurid skeleton. The vertebrae at the front of the back were slightly taller, but much longer than those at the rear, whereas in Giraffitan, the front vertebrae were much taller, but only slightly longer. The vertebral bodies were elongated and roughly circular in cross-section, and the openings on their sides for air sacs were larger than in Giraffitan. The sideways projections that connected to the ribs were horizontal, unlike the upward-angled projections in Giraffitan. The tall neural spines stood vertically in side view, twice as wide at their bases as at the tops, while those of Giraffitan leaned backward and did not widen at the base. Viewed from the front or back, Brachiosaurus's neural spines widened gradually toward the top, giving them a paddle-like shape, whereas in Giraffitan, the widening happened abruptly at the uppermost part. The neural spines also had large, triangular, rough-textured surfaces at both front and back, unlike Giraffitan, where these surfaces were smaller and semicircular. Thin, bony sheets called laminae connected the vertebral processes. Brachiosaurus lacked postspinal laminae, which ran along the backs of the neural spines in Giraffitan. Other laminae, stretching from neural spines to rib projections, were fused with laminae connecting to the rear articular processes and ended midway up the neural spines, whereas in Giraffitan, they reached the top. Finally, Brachiosaurus lacks three unique lamina details found in Giraffitan's dorsal vertebrae, further distinguishing the two giant cousins. In Brachiosaurus, air sacs were not just limited to the vertebrae, but also extended into the ribs, creating a complex system of lightweight structures throughout the skeleton. The air sacs entered the rib bones through a small opening on the front side of the shafts. In comparison, in Giraffitan, these openings were found on both the front and back of the tuberculum, a small bony projection that connected with the vertebrae. In 1988, the paleontologist Paul suggested that the ribs of Brachiosaurus were longer than those of Giraffitan, although this idea was later questioned by Taylor in 2009. Behind the main backbones, the sacrum, the fused set of vertebrae supporting the hips, consisted of 5 sacral vertebrae joined together. Like Giraffitan, Brachiosaurus had a wide sacrum with very short neural spines, though the poor condition of the Giraffitan sacral fossils makes detailed comparisons difficult. From the tail, only the second caudal vertebra was well preserved. This vertebra was slightly concave at both ends, lacked side openings, and had a short, rectangular neural spine leaning backward, similar to Giraffitan. However, Brachiosaurus's second caudal vertebra had a taller neural arch, making the bone about 30% taller than in Giraffitan. Its central body lacked the side depressions seen in Giraffitan, and when viewed from the front or back, the neural spine widened toward its tip, to roughly 3 times its narrowest width, a feature not seen in Giraffitan. The neural spines leaned back at about 30 degrees, more sharply than Giraffitan's 20 degrees. The tail ribs projected out to the sides rather than tilting backward, and the articular facets of the rear processes faced downward, while in Giraffitan, they were more sideways. In addition to these facets, the hyposphene-hypantrum articulation created another connection between vertebrae, adding rigidity to the spine. This feature was much more pronounced in Brachiosaurus than in Giraffitan. The shoulder blade of Brachiosaurus included a semicircular coracoid that was taller than it was wide. Compared to Giraffitan, its side profile was straighter where it connected with the scapula. The part of the coracoid that formed the shoulder joint was thicker and angled more outward, possibly indicating that the forelimbs were held more sprawled. The humerus, or upper arm bone, measured 204 centimeters in length, though erosion had removed part of the lower end. Its estimated original length was 216 centimeters. This bone was narrower than in most sauropods, measuring only 28.5 centimeters at its narrowest point, yet it was about 10% thicker at both ends than Giraffitan's humerus. A small bulge at the upper end, visible from the side, was unique to Brachiosaurus and absent in Giraffitan. The pelvis also revealed distinct differences. The ilium featured an ischiotic peduncle, a downward projection connecting to the ischium, which extended farther than in Giraffitan. Where Giraffitan had a sharp notch at the rear of the ilium, Brachiosaurus's notch was more rounded. The upper surface of the hind part of the ilium had a pronounced bump, or tubercle, not seen in other sauropods. The femur, or thigh bone, was very similar to that of Giraffitan, but slightly thicker and measured 203 centimeters long. Like Giraffitan, it was strongly elliptical in cross-section, more than twice as wide from front to back as it was from side to side. The fourth trochanter, a bulge on the back of the femur for muscle attachment, was larger and placed lower on the bone, anchoring the caudofemoralis muscle from the tail, which pulled the upper leg backward. At the bottom of the femur, the condyles were equally wide, unlike in Giraffitan, where one was wider than the other, and they did not project as far backward. Based on reconstructions by Carpenter and Tidwell, the Felch Quarry skull assigned to Brachiosaurus measured about 81 centimeters from the occipital condyle at the back to the front of the premaxilla, making it the largest sauropod skull known from the Morrison Formation. Other estimates by Demick and Carano suggested a slightly shorter length of 70 centimeters, and, if proportionally similar to Giraffitan, a height of 55 centimeters and a width of 35 centimeters. The skull, like Giraffitan's, was tall, with a long snout extending about 36% of the total skull length in front of the nasal bar between the nostrils. Seen from above, the snout appeared somewhat blunt, and due to its angle, gave the impression of pointing downward. The openings in the skull for muscles, the dorsal and lateral temporal fenestrae, were large, likely reflecting the strong jaw muscles. The frontal bones on top were short, wide, and fused to the parietals, which were also fused. The surface between the dorsal fenestrae was wider than in Giraffitan, but narrower than in Camarasaurus. Unlike Giraffitan, the suture between the frontal and nasal bones was U-shaped, with frontal bones extending forward over the eye sockets. The premaxillae were longer than in Camarasaurus, sloping gently toward the nasal bar, forming a long snout. The maxilla was deep, thick along the tooth sockets, and thinner toward the top. The interdental plates were thin, fused, porous, and triangular, with tiny openings between them for erupting teeth. In front of the nostrils, the narial depression was long, shallow, and less developed than in Giraffitan, but it contained a subnarial fenestra much larger than in Giraffitan or Camarasaurus. The lower jaw bones were strong, but less so than in Camarasaurus, with a gently arched top edge. They contained oval interdental plates with diamond-shaped openings and a Machelian groove that continued along the lower jaw. Each maxilla held space for 14 to 15 teeth, compared to 11 in Giraffitan and 8 to 10 in Camarasaurus. The replacement teeth were thick, lacked serrations, and were larger than in Camarasaurus. Premaxillary teeth were spoon-shaped with a longitudinal ridge. The lower jaw had similar capacity for about 14 teeth. The tooth rows ended well in front of the antorbital opening, unlike Camarasaurus and Huincul, where the rows extended just beneath it. Overall, Brachiosaurus had more complex teeth than many other sauropods. When first describing Brachiosaurus in 1903, Riggs considered it clearly a member of the sauropod group. He compared it with Camarasaurus, Apatosaurus, Atlantosaurus, and Amphicoelias, but found their relationships uncertain due to limited fossil overlap. By 1904, after examining the vertebrae more closely, he concluded that Brachiosaurus was closer to Haplocanthosaurus, sharing a single line of neural spines and wide hips, and he established the new family Brachiosauridae, with Brachiosaurus as the namesake genus. Haplocanthosaurus was seen as a more primitive member, with Brachiosaurus being a more specialized form. In 1914, Janensch, studying Brachiosaurus bronsai and B. frasi, noted that the unusually long humerus was shared by all three species and by the British Pelorosaurus, and also to a lesser degree in Cetiosaurus. He grouped these genera closely and, in 1929, assigned them to a subfamily, Brachiosaurini. Throughout the 20th century, other sauropods, such as Astrodon, Bothriospondylus, Pelorosaurus, Pleurocoelus, and Ultrasauros, were sometimes added to Brachiosauridae, although most of these assignments were later considered doubtful. In 1969, Kingham even combined several species into Astrodon altathorax, a view not widely accepted. From the 1990s onward, computer-based cladistic analyses allowed scientists to propose evolutionary trees with more precision. These studies questioned whether Brachiosauridae was a natural group. By 1993, Salgado suggested that traditional brachiosaurids were an artificial grouping. In 1997, he proposed that these species were early branches of the larger Titanosauriformes group, rather than a separate lineage. Subsequent analyses confirmed that while some genera could be included in Brachiosauridae, their exact positions varied. A study in 2010 recognized Abitosaurus and Brachiosaurus as brachiosaurids, including B. branchi, but Taylor in 2009 separated B. branchi into the new genus Giraffitan, treating both as sister groups. Later studies placed Brachiosaurus and Giraffitan on different branches of the evolutionary tree, highlighting the ongoing complexity in understanding these giants. Seismosaurus was an enormous plant-eating dinosaur that roamed the lands of western North America during the late Jurassic period, which stretched roughly from 161 million to 145 million years ago. It belonged to the lizard-hipped dinosaurs, scientifically known as the order Saurischia, and more specifically to the long-necked, four-legged suborder called Sauropoda. When first studied, scientists thought that Seismosaurus hallorum, its full scientific name, was closely related to another giant dinosaur called Diplodocus. By the early years of the 21st century, however, most experts agreed that Seismosaurus was not a completely separate species, but rather a very large type of Diplodocus. Because of this, it was often unofficially renamed Diplodocus hallorum, though the old name Seismosaurus is still commonly used. This dinosaur was among the longest creatures to ever walk the earth. Fossil evidence suggests that adult Seismosaurus individuals measured around 110 to 120 feet in length, which is approximately 33.5 to 36.5 meters, although some might have grown even longer. Early estimates of its weight suggested it may have weighed 100 tons or more, but more recent studies indicate it was much lighter than that. The name Seismosaurus, meaning earth-shaking lizard in Latin, came from the idea that this massive creature would make the ground tremble with every step. Seismosaurus had a remarkably long, slender neck that ended in a small, delicate skull, about the size of a modern horse's head. Some scientists propose that the dinosaur's neck usually stayed close to horizontal so that its heart could effectively pump blood all the way to its head. Its tail was equally impressive, long and flexible like a whip, while its thick, stubby legs ended in 5 toes on each foot, one of which had a claw. As a quadruped, Seismosaurus walked on all 4 legs. Its diet consisted of a wide variety of plants, including conifers, ginkgos, cycads, horsetails, and ferns. Fossil discoveries show that it also swallowed stones, known as gastroliths, which helped grind the tough plants in its stomach, much like modern birds use small rocks to aid digestion. In one fossil specimen, paleontologists counted more than 240 gastroliths, ranging in size from that of a peach pit to the size of a small grapefruit, all smooth and rounded from use. For a long time, scientists believed that western North America during the Jurassic period, which lasted from roughly 201 million to 145 million years ago, was a completely tropical region, full of lush greenery and constant water sources. They imagined that giant sauropods like Seismosaurus had plenty of food and never wandered far from water. In more recent decades, however, researchers have suggested that the area was more like a vast desert, broken up by narrow strips of forests and vegetation along rivers and streams. Herds of Seismosaurus likely roamed continuously within these forested areas, feeding until most of the plants were eaten, and then they may have traveled across dry desert regions, searching for new feeding grounds. The first clues to Seismosaurus came in 1979, when a group of hikers discovered large tail vertebrae embedded in a sandstone mesa in New Mexico in the United States. American paleontologist David D. Gillette began digging up these fossils in 1985. Believing he had found a new species, he formally named it Seismosaurus in 1986 and provided a detailed description in 1991. Excavating the rest of the skeleton was especially difficult because it curved deeply into the rock of the mesa. Gillette traced the remaining bones using seismic tomography, a technique that sends sound waves into the ground to detect hidden structures. This marked the first time such technology was ever used to locate dinosaur remains. There are several ideas about how Seismosaurus might have died. Fossils at the site included a large tooth from a meat-eating dinosaur, suggesting that predators like Allosaurus may have attacked it. Other paleontologists think a more likely scenario is that the dinosaur died of natural causes and scavengers removed its flesh, during which one carnivore lost a tooth. This would explain why the skull and jaws were missing and why some neck vertebrae were disconnected. Another theory suggests that a large gastrolith found among the remains might have gotten stuck in the dinosaur's throat, blocking its airway and causing death. The discovery of Seismosaurus was thrilling for paleontologists for many reasons. Many of the vertebrae were still connected as they had been in life, which is extremely rare. Even more remarkable, the bones had not fully fossilized. They retained much of their original composition and were light in color, instead of the usual dark brown or black of most fossils. The bones had also survived many years exposed on the surface of the earth without crumbling, defying the normal destructive forces of nature. This extraordinary preservation gave scientists an unprecedented glimpse into the anatomy of one of the largest creatures ever to walk the planet. Amphicoelias, whose name comes from Greek words meaning hollow on both sides, was a plant-eating sauropod dinosaur that roamed what is now the state of Colorado in the United States during the late Jurassic period, roughly 150 million years ago. Compared to some of its giant relatives, Amphicoelias was of moderate size, stretching about 18 meters or 59 feet from head to tail and weighing around 15 metric tons, or about 17 short tons. Its hind legs were long and slender, giving it a graceful, almost delicate appearance, while its front limbs were proportionally longer than those of its close relatives, giving the animal a slightly more upright stance. The first fossil that gave Amphicoelias its name belongs to the type species Amphicoelias altus, now catalogued as specimen number 5764 at the American Museum of Natural History. When it was first described by the American paleontologist Edward Drinker Cope, shortly after its discovery in 1877, he recorded that it included many back vertebrae, a single pubis, and one femur. Later, after the fossils were purchased and catalogued by the museum, paleontologists Henry Fairfield Osborn and Charles Mook reassessed the specimen and listed it as containing only 2 vertebrae, a pubis, a femur, a tooth, a scapula, a coracoid, an ulna, and a second femur. Some of this extra material, not mentioned by Cope, was found nearby and bore a strong resemblance to Diplodocus, a close relative of Amphicoelias. However, later researchers, including Emmanuel Chopp and his colleagues, questioned whether all of these bones truly belonged to Amphicoelias. In the same year that Amphicoelias altus was described, Cope also named a second species, Amphicoelias latus, based on a femur and tail vertebrae. Almost half a century later, in 1921, Osborn and Mook concluded that this material actually belonged to another sauropod, Camarasaurus, a view that other scientists have agreed with over time. A year after that, in 1878, Cope named a third species, Amphicoelias fragilis, based on a single enormous dorsal vertebra that has since been lost. Early reconstructions suggested this vertebra would have been about 2.7 meters, or roughly 8 feet 9 inches tall, and estimates of the dinosaur's full length ranged between 40 and 60 meters, or 130 to 200 feet. These extraordinary numbers, which would have made it the longest known dinosaur, were largely ignored because the fossil was so incomplete. In 2018, Kenneth Carpenter reassigned Amphicoelias fragilis to a new genus called Brachiosaurus and classified it not as a diplodocid, but as a member of the Brachiosaurids, a different group of long-necked dinosaurs. The discovery of Amphicoelias began in 1877 when a local fossil collector named Oromel William Lucas uncovered a range of bones in rocky outcrops near Canyon City, Colorado. Among these finds were fossils Cope would later identify as Laelaps trihedrodon, Camarasaurus supremus, and Caulodon, which he mistakenly thought came from the younger Cretaceous Dakota Formation. Among the bones found was a remarkable specimen of multiple dorsal vertebrae, a pubis, and a femur, unearthed by Lucas's brother-in-law, Aaron Ripley, in a site called Quarry 12. These fossils were sent to Cope on October 21, 1877. By December of that same year, Cope named them Amphicoelias altus, placing them in the sauropod family, which he believed included lightly built giants with solid limbs, related to nearby Camarasaurus. Cope sold his collection to the American Museum of Natural History in 1895, and before his death in 1897, he collaborated with the museum artist Charles R. Knight to produce life illustrations of some of his discoveries, including Amphicoelias. Cope noted several features that distinguished Amphicoelias from Camarasaurus. For instance, the vertebrae of Amphicoelias were amphicoelous, meaning both ends of each bone were concave, unlike Camarasaurus, which had vertebrae with a ball and socket front end. Cope even proposed two separate families, Amphicoelidae for Amphicoelias and Camarasauridae for Camarasaurus, based on these differences. Other distinctions included smaller openings in the vertebrae and thinner limb bones in Amphicoelias, though both families shared certain accessory joints in the neural arches that limited spinal movement. Later researchers, including Othniel Charles Marsh in 1881, found that many of these features were not unique and appeared in other sauropods as well. Amphicoelias latus, originally named for four tail vertebrae and a robust femur, was eventually reassigned to Camarasaurus supremus, while Amphicoelias fragilis, known only from an enormous dorsal vertebra, became Marapunosaurus. The exact size of these giants remains uncertain due to incomplete fossils, but estimates suggest that A. fragilis, if reconstructed from related species, could have reached awe-inspiring lengths far surpassing any other known dinosaur. The anatomy of Amphicoelias altus is partly known from the fossils preserved. Its dorsal vertebrae are compressed in the center with large lateral cavities and tall neural arches. Ridges run along the sides of the neural spines, which end in wide tips. The forelimb bones, although only partially preserved, suggest a structure similar to Diplodocus but more robust, with scapulae thicker than those of Diplodocus, a rounder coracoid, and an elongated ulna. The pubis is long and thick, while the femur is slender, gently curved and approximately round in cross-section, measuring about 1.5 meters or 5 feet in length. Over the years, debates have continued over whether Amphicoelias is truly a separate genus or simply an earlier name for Diplodocus. Some researchers argue that variations in the fossils are minor and might reflect differences among individuals rather than species. Others maintain that Amphicoelias has distinct features, particularly in its vertebrae and forelimb proportions, justifying its recognition as a separate genus. Recent phylogenetic analyses place Amphicoelias as one of the most primitive members of the Diplodocid family, showing a mix of traits found in both apatosaurans and diplodocans, which highlights its importance in understanding the evolution of these long-necked giants.